Okay, here's some information about the test. We've talked about this a little bit previously, but just as a refresher, there will be 35 questions, one from each of the question groups you've studied. You need to get 26 correct to pass the test. The test is not timed, so relax and enjoy it. After you pass element 2, the technician test, give element 3 a try for the general. You may get lucky and surprise yourself and end up a general, and it doesn't cost anything. You pay for the test session, not for the individual test. And the test team needs to send in some failures to make them look honest, so you can help them look honest if you fail it too, which is always a good thing. Test-taking skills. Most of you probably know these, but let me review them with you quickly anyway. All tests are reading tests. So be sure you carefully read the question and all the answers before you mark your answer sheet. Be sure you're marking the correct number on the answer sheet for your question. Occasionally you'll get off track, especially if you skipped a question, and you'll be putting the answer for number 26 in the space for number 25. And that usually does not go well. If you go back through your test, be hesitant about changing answers. Your first response has a good chance of being right. Don't change unless you're sure. I saw a young fellow last October up at Waimea at the testing session there talk himself out of a passing score because he changed some correct answers to incorrect answers. He changed just enough to fail the test. So unless you're sure that your first response was bad, don't change it. Okay, here we start the actual review and with some general principles. And if you have your review sheet with you, you can follow along on this. These are mostly in the same order that they are on the sheet. They are, if they're not right in the same order, they're right close there. So you should be able to find it okay. Radio waves are electromagnetic waves. You'll remember they have both an electric and a magnetic component to them. We call them electromagnetic waves. Another general principle that you should understand is that as frequency increases, wavelength decreases. And I found a really great graphic for that. Here you see the higher frequency with the shorter waves, and here you see the lower frequency with the longer waves. Now, one reason I really, really like this graphic is they made both of those pictures the same length. Okay, and this length here represents not only the physical length of the wave, but it also represents time. Okay, because radio waves travel at a fixed rate, and they travel at the same rate regardless of their frequency. Well, so let's take a look at something here. Let's pretend that this length of time is 1/millionth of a second. Okay, 1/millionth of a second. Same thing down here, 1/millionth of a second. All right. Now, if this is 1/millionth of a second, I have 12 waves there in my 1/millionth of a second, which means that the frequency of this is 12 megahertz. Okay. Here I have 5 waves in my 1/millionth of a second, which means the frequency here is 5 megahertz. So you can see very graphically the difference in wavelength between the higher frequency 12 megahertz with the shorter waves and the lower frequency 5 megahertz with the longer waves. In direct current, electrons flow in only one direction. And one of your keys to that is, if you look at a battery, it has a plus and a minus mark on it. If you look at a DC power supply, it has a plus and a minus pole on it. And that tells you that you have direct current, like right here, and that the electrons are all flowing in the same direction. And if we put that direct current onto a scope, you're going to see just a line there showing the voltage that's coming out of your direct current supply, whether it's a battery or a power supply or something like that. Alternating current regularly reverses the current flow. The electrons flow one direction and then they flow the other direction. And if you put that on a scope, you will see this voltage going positive to a peak, dropping back, going through zero, going negative to a negative peak, going back through zero, and it continues to do this. This is alternating current. So the voltage is constantly changing, and it does this at a regular rate, which we call the frequency. Okay? So alternating current reverses the current flow, the direction of the electrons are moving, on a regular basis. Technicians mainly operate in the 6-meter band and higher frequencies, and I've stuck this in here. This is on your blue sheet, of course, you'll remember. And just to show you what those bands are, we have the 6-meter band, we have the 2-meter band, we have the 1.25-meter band, the 70-centimeter band, 33 centimeters, and 23 centimeters. So these are the frequency bands that technicians principally operate on. They're the only bands that are addressed in the technician test. Okay, here we continue with a 1.25-meter band. You should know what these band limits are, incidentally. You should know these numbers here. The 1.25-meter band has that segment from 219 to 220, and then from 222 to 225. The 70-centimeter band, 420 to 450 megahertz. 23-centimeter band from 1240 to 1300. You can ignore the 33-centimeter band. There are no questions on the test about the 33-centimeter band. So you should know the 6-meter band is from 50 to 54 megahertz. 2-meter band is 144 to 148, and then also these. The 6-meter, 2-meter, and 1.25-meter amateur bands have mode-restricted subbands, and what we mean by that is that here I have this band from the 6-meter band from 50 to 54 megahertz, and I can do all of the kinds of emissions that hams use, voice and data and whatever else, in this part of the band, but down here I have a mode restriction where I can use only Morse code, only CW on and off Morse code keying. Okay, so that's a mode restriction in the 6-meter band, and this is a mode restriction, a similar one, in the 2-meter band. And then there's also a mode restriction here in the 1.25-meter band, but it's a different mode restriction. But anyway, these 3 bands have mode restricted mode restricted subbands. So this subband here, this subband here, this subband here. There are restrictions on what kind of communications you can carry on. The mode restrictions on 6 and 2 meters are CW, Morse code only, right here. And data is the only kind you can operate in this segment of the 1.25-meter band. Okay. VHF frequencies are from 30 to 300 megahertz. I've underlined the megahertz here because you'll remember I told you that one of the questions, if you should happen to get it on the test, offers you both the answers of 30 to 300 megahertz and 30 to 300 kilohertz. So read carefully. And the VHF frequencies are from 30 to 300 megahertz. UHF frequencies are from 300 to 3,000 megahertz. There's a magic number of 300. You can divide 300 by the frequency in megahertz to get the wavelength in meters, or you can divide 300 by the wavelength in meters to get the frequency in megahertz. Let's take a look here at the 6-meter band. 300 divided by 50 megahertz gives you 6 meters. 300 divided by 6 meters gives you 50 megahertz. Okay, now that's a nice clean one. Everything works out right. The numbers all match and everything. Not all the bands are that exact, though. What we call the 2-meter band, if you calculate it out, is actually 150 megahertz. And the band is calculates out to 150 megahertz. The band is actually below that at 144 to 148, but it is close. And so we call this band 144 to 148 the 2-meter band, even though it's not exactly 2 meters in wavelength. But using this can get you close. Okay, let's talk about power, voltage, current, and resistance. Power is the amount of work that's being done or produced in a circuit. And our power formula, our pie chart here, we have power in watts equals the current in amps times the electromotive force in volts. And the power formula here, if we know power, we can divide it by, if we know power in volts, we can divide volts into power to get the current. If we know power and current, we can divide current into power to get the volts. If we know current and volts, we can multiply them together to get power. So that's how that formula works. Okay, in a similar fashion, we have Ohm's law, which also gives us a pie chart, but this time it doesn't say pi. Electromotive force in volts equals current in amps times resistance in ohms, okay? So, and again, this states the same thing. Electromotive force, pressure, or voltage is equal to the current times the resistance to the flow. And this works out in several different formulas. Voltage is equal to amps times resistance, current times resistance. Current is equal to voltage divided by resistance. Resistance is equal to voltage divided by current. And here's a good summary right here of that. And again, in the chart, if you cover up the one you want to know, for example, if you don't know the amps, you can divide the voltage by the resistance, and it will give you the current in amps. Okay, and they just made a little note here that when you put the letters into that, if you put them in an alphabetical order. We use multipliers and dividers on the units to adjust the units in scale for what we're measuring. For instance, for radio, we don't talk about hertz because it's much too low in frequency. We talk about thousands of hertz or millions of hertz, kilohertz or megahertz. Okay, so if we use the prefix mega, that means 1 megahertz is equal to 1 million hertz. Okay, the prefix mega means times a million. Kilo means times 1,000, so 1,000 hertz means or is equal to 1 kilohertz. Going the other direction to the smaller units, we use milli for 1,000th. So we might say a milliampere when ampere is too big a unit for our measurement. We might say microvolt, a millionth of a volt, if a whole volt is too much. And we actually do measure microvolts. We talk about the sensitivity of receivers and that sort of thing in fractions of microvolts. So it is a useful unit. And then pico is 1 trillionth. It's a millionth of a millionth of whatever unit it is. Principally, it is farads, the unit of capacitance. And 1 picofarad is equal to 1 trillionth of a farad or 1 millionth of a microfarad. Okay, and these are actual units that you'll run into in handling capacitors. It used to be when I was first in this, we didn't have picofarads. We talked about microfarads, millionth of a millionth of a farad. But the term now is picofarad for a millionth of a millionth.